We're on live now. So, hello, good afternoon, everybody. Today we have another meeting, another group meeting. Today we're going to have two presentations. One is made by Jéssica. She will talk about the Helicidade and Quiralidade. She is an undergraduate student. And the other presentation will be made by Maria Jose about the electron fiber violation. So first, we're going to have Jessica's presentation. So let's hear what she has to say. Yes.
Hello, my name is Jessica, and in today's presentation, I'm going to talk about helicity and quirality, which are very important particle properties. I'll make first an introduction, very silly concepts, and then I'll profound the concept in the physical way and tell the difference between them because they sometimes match and sometimes they are different. Okay, quirality is more of a transformation property in the mathematical way, not really easy to explain in physical terms compared to helicity, because helicity is a projection of the spin onto the direction of momentum. So the quirality is separated by left and right-handed. When we have, okay, I'll first show the matrix because it's important to show the gamma 5 matrix. Here we have the gamma 5 matrix, which doesn't seem much important, but it is very important. You will know later. It is very important. The eigenvalues of it is very important because this matrix right here has +1 and -1 eigenvalues. +1, we have right quirality, and -1, we have left quirality. Here we have the limit, the ultra-relativistic limit when energy is much larger than mass, when we have a massless particle, for example, and we have a fact for 4 out of 16 matrices of the Dirac equation is not null given all. Wait. They give non-zero values, which reveals something about the structure of QED. So this reveals that QED is chiral, but it's really chiral, and is it always chiral? Okay, here we have the comparison of the spinors of the Dirac equation, the solutions of the Dirac equation for the particles, which are represented by this U here, and for antiparticles, this V here. The N is for normalization and also the square root of E. And here we have in orange all of our matrix, of our gamma 5 matrix. And it's very, very similar, which could prove that our QED is chiral. Let's now talk about the quality projection operators. They separate left-handed and right-handed components of a Dirac spinor. Here for the right, yes, here it is our gamma 5 matrix. Here in the Dirac-Pauli representation, and here's some properties that are very similar for both left and right-handed. Quirality is, I put this phrase here, but I think it's maybe unorganized, but you will understand it. The key difference between helicity and the quirality is when we have a massive particle, and this particle is a reference frame. It is moving in a reference frame. We are comparing the helicity and quirality are the same only if we have massless particles, because when we have mass, the mass term in the Lagrangian QD breaks the symmetry. So if we boost onto a reference frame and we go faster than a particle, we observe it, its helicity changes, it flips. But if we have a massless particle, the helicity stays the same because we do not have a reference frame faster than our particle, because the particle, when it's massless, it is in the light speed. So we do not have a reference frame faster than the light speed. But chirality does not depend on perspective. It is only a property, as we say, based on Lorentz symmetry. Okay, so talking about chirality and QD. For mass tending to zero, the components of the fermion field, left and right-handed, behave almost independently. But for massive particles, chirality is not conserved. The mass term in the QD Lagrangian, it breaks the symmetry. And I will tell you, I forgot to tell, but I'll tell now. This is the helicity operator. It's the projection of the spin onto the direction of the momentum, right? Okay, what I haven't told you is that when it's positive, we have right chirality, and when it's negative, we have left chirality. The particle's left chiral. So, how do different forces treat chirality? The electromagnetic forces don't prefer one. It treats left and right chiral particles the same, but the weak force left one by the side, as I might say. They are different. They are treated differently. And the best example I can say is the neutrinos. Neutrinos are very, very low in mass. That's almost massless. So the gravity term does not matter much. So the only term that matters is from the weak force, which tell us the neutrinos are left chiral. But what if we had antineutrinos? Antineutrinos would be right chiral, right? We only observe left neutrinos because it's not, the parity is not conservated. So in conclusion, helicity and chirality are the same when we have massless particles, but when we have mass, they mix up. So when we have mass, helicity flips, and chirality, for example, if we have the neutrino I talked about, that is left chiral, if we have a neutrino left chiral, we not necessarily a neutrino, let's say a particle left chiral, if we had mass in that particle, it should not really intrinsically be left chiral. It could be, but it could be right chiral. Thank you for your attention.
Time for questions.
So, Jessica, could you explain why exactly neutrinos behave differently?
The neutrino reacts with the weak force and by the gravity, but the gravity is weaker because the neutrinos have almost zero mass. So the weak force tells us that they appear only in the left chiral side. We only observe left chiral neutrinos.
Yeah, so that's what you said. So neutrinos are left-handed, right? So they do interact with the W boson. So why they are different on the weak force?
This part I don't know.
On this?
Probably because the structure probably because the weak force has different structure.
Go.
I don't understand the question. Like, why are they different?
Yeah, she's saying that how do different forces treat chirality? And then she's saying that neutrinos have a different chiral nature, therefore they're treated differently via the weak force.
Oh, because the weak decay W interaction that changes the flavor of the particles only happens with left-handed particles.
Yeah, the neutrinos
Yeah,
are left-handed.
neutrinos are only left-handed.
Yeah.
That's why they are only left-handed.
Yeah, but and what about the charged leptons? They're also left-handed. No?
Yeah, but they are also they're right and left-handed. That's why they have masses, because they have the two chiralities.
Okay, but how is that different regarding the W boson decay?
Because why the W boson only?
Yeah, so for instance, if you're saying that, I'm just stating what you said, right? She's saying that neutrinos are left-handed, okay?
Yeah.
Electrons can also be left-handed. And W's decay to leptons and neutrinos, right?
Mhm.
To both of them. So why neutrinos are different? That's what she's saying, right? They are different. They are both the left-handed leptons, charged leptons, and neutrinos are present in that decay, right?
But the point is, she's saying the neutrinos is exclusive, right? Exactly what you're saying.
Why neutrinos are exclusive?
Yes.
They are not exclusive. So neutrinos, they are involved in all weak interactions, all of them. So the weak force does not change neutrinos in this way. But the W boson only interacts with left-handed fields, but neutrinos are left-handed. So the weak force does not treat neutrinos differently because they are left-handed. It's okay. But the electromagnetic force, yes, then is different. The electromagnetic force does not interact, neutrinos do not interact with the electromagnetic force, right? Because they don't have charge.
Yes.
But via the weak force, no, it's the same. Right? If she was talking about right-handed neutrinos, then it's a different story. Because right-handed neutrinos do not talk to the W boson. But these neutrinos we know, yeah, they talk to the W boson. No problem. So just perhaps the correction would be that the neutrinos do not feel the electromagnetic force
Okay.
because they don't have electric charge. Okay? In the weak force, they are just as the same as the charge level. And the Z boson, decays into neutrinos? Yes, it does decay.
She shouldn't be referring to neutrinos specifically, because the idea is to how the different forces treat chirality. So in electromagnetic force, the chirality term, the complement is the same for both chiralities. But in the weak force, especially in the charge current,
With the charge current. Yeah.
I think that's the point that she should bring in this point. With the charge
She doesn't know
current,
that yet. Then that's why I didn't.
I would ask, but in the charge current, they treat it differently.
Yeah.
But for example, in the neutral current, they treat it the same.
Mhm.
So they have both the photon term, for example,
Exactly.
is the electromagnetic term, and the Z should be the same. So I think she should point that the charge in the specifically in the weak force in the charge current,
Charge current within the weak force.
yeah, they would differ from the electromagnetic force in the chirality sense. Did you understand? Or I just
Yeah, perhaps it is better to explain her, but it's too complicated.
Maybe the thing that there was a misunderstanding in the. I mean, I'm trying to understand why we put neutrinos there is specific. Maybe it's because they are only left-handed. They doesn't have a right-handed neutrino, so they're specific because we only have left-handed. But in this slide is a
Yeah.
bit lost because
yeah,
it's not dependent on how the force is collected.
because the neutrino is left-handed, but electrons is left-handed as well.
Yeah, exactly.
Eons are left-handed, so what's the point?
Yeah, exactly. Okay.
One question then?
And one thing for all of you to know, so if you have attended a course in particle physics, whether it was with a good professor or with a bad professor, it doesn't matter. You have to know by heart the Lagrangian of the charge current. You have to know it by heart. You can say, I think it has. You have to know. You have to know. There is no other way. Because it's your field. Right? So it's your field. That's what you'll be doing for a living. So it's your field. So you must know. There's no other option. It's some things you have to memorize. Not many, but some things you do have to memorize. It's like, okay, you work in particle physics, you don't know the basic Lagrangian of the stellar model.
So let's finish, Jessica. So that was for Jessica. So let's end this screen here. We like and subscribe and see you. Right now